So let's look at an example of Faraday's law. And this is out of the book. So we're looking down on an elastic conducting loop with resistance R equals 2 ohms, immersed in a magnetic field. The magnetic field, their field's magnitude is uniform spatially but varies in time according to this formula. B function of t is equal to alpha t, where alpha t is 0.6 teslas per second. And the area of the loop is increasing at a rate of a function of t is equal to a naught plus beta t. And a naught's 0.5 meters squared, and beta is equal to 0.7 meters squared per second. So we want to find the magnitude and direction of the current when viewed from above the page, when and we want to calculate the value at t equals 2 seconds if the field is parallel to the plane of the loop, or if it's perpendicular with the magnetic field down. Well, for part A, this is very simple. It says it's parallel to the plane of the loop to the right. So for A, there is no induced current or induced potential or EMF. I don't really like using that term, but they use it. So that part was easy. Now for part B, well, first we have to write our magnetic field, so that's B function of t, and that's going to be equal to 0.60 teslas per second times t, and our area is going to be equal to 0.50 meters squared plus our beta is 0.70 meters squared per second times t. And now I need to multiply those together to get the flux. This is a lot of writing. Okay, now I have 0.60 times 0.50, and that's going to give me 0.30, and then I'm going to have the units Tesla meter squared over seconds times t plus 0.42, actually I want to put these in parentheses, 0.42, and it's going to be Teslas meter squared per second squared times t squared. And now my induced potential is going to be equal to the derivative of phi, function of t, and that's just going to be equal to, well, this part's easy because it's just t, so it's going to be 0.30 Tesla meters per second Tesla meter squared per second. And our formula for, our result for the second one, well, I'm going to have this 2 down here. So that's going to give me 0.84. And then I'm going to have a Tesla meter squared per second times, it's second squared, times t. So my units are consistent because here I have Tesla meter squared per second. Here, when I multiply by seconds, I'm going to have Tesla meter squared per second. So that gives me what I need. Oh, and I forgot the negative sign here. So we'll put that in there. And so now, when I put in E at 2 seconds, that's going to be 0. I need to put a negative in here. So negative 0.30 Tesla meter squared per second plus, and I'm going to have, sorry, it should be minus. Carry my minus through. And it's going to be 2 times, oh, I'm sorry. No, I have that right. I'm sorry. So minus 0.84 Tesla meter squared over second squared times 2 seconds. And when I calculate that out, I get just about a negative 2 volts, 1.98. So Tesla meter squared per second is the unit for volts or potential. And my current is just going to be equal to my induced potential at my value of 2 seconds over the resistance, which was 2 ohms. And that gives me about minus 0.99 amps. So if I'm looking at a coil and I'm looking so that the magnetic field's going inside or into the page, then if I put my fingers in the direction of the field down here, my fingers go through the field, my thumb's going to point in this direction. That would be normally how my eye would go. And if I point up to put my fingers through the loop around this wire, it would go in this direction. So this I, the way I would do the right-hand rule, is going in the clockwise. So the right-hand rule says current is in the clockwise direction, so the induced current is in the counterclockwise direction. So what are we doing here? Well, we're saying that if I had a current, this I, flowing in a wire loop, then the magnetic field would be in this direction. So I is the current producing the magnetic field, and I induced in the counterclockwise direction is the current produced by changing flux. And so the induced current is going to be in the opposite direction of a magnetic field created by a current.